Okay, let's talk about atomic structure. So, atomic structure has to do with atoms, and atoms are the building block of matter. So, you can see here I've written that atoms are small bits of matter. And what is matter? Matter is the stuff that makes up everything. Okay, so before we could see small enough to find out that there were atoms and there are even particles smaller than that make up the atoms, we just said like everything's got to be made of something, that something's called matter. Okay, so fast forward to now, and we know that there are these small things that make up all stuff that's made from matter. And those things are called atoms, which are small bits of matter, or the building blocks of matter, if you will. Inside of those atoms are these three subatomic particles that we're going to focus on. There's other stuff, but let's focus on these three for now: protons, neutrons, and electrons. So here I've drawn a really crappy model of an atom, and it's called a Bohr model. It's named after some old white guy, Niels Bohr. Doesn't matter too much. What does matter is that you can see here in the center, there's this nucleus. This is not a cellular nucleus. There's not like cytoplasm and mitochondria and vacuoles and stuff in there. There's not. It's not in there. It's in fact really, really, really small, and it's only made up of two things: protons and neutrons. The nucleus actually only has protons and neutrons in it. It's a tiny little part of the atom, and atoms are very, very tiny. In fact, cells and all the things I told you, those organelles that I was listing that are in the cells, are made up of atoms also. So atoms are really, really small. So subatomic particles are incredibly small, much smaller than atoms, even because they make up atoms. So, anyway, our nucleus has protons, which have a positive charge and a mass of 1 atomic mass unit. The unit doesn't really matter, but we call them AMUs, atomic mass units. And neutrons, which are neutral, have no charge and have a mass of 1. Okay, so protons and neutrons in the nucleus have mass. So, if you look at this nucleus here, there's 3 protons and 3 neutrons, so it have a mass of 6. Then, flying around the outside on these orbital paths are these things called electrons, which are negatively charged and have basically no mass. They do have a mass. It's really, really small. So we're going to say no mass for now. Okay. Now, here's the deal about electrons. The odds of an electron actually being where this circle is, that's what this blue arrow is pointing to this electron right here, are actually kind of low. So electrons are not taking these orbital paths like planets around the sun. In fact, they're flying around randomly in a cloud. But that's really hard to draw. So instead, we use this Bohr model to kind of show you that there are these different levels that these electrons can be in. And these levels are considered energy levels or shells. And we're going to learn more about those as we go. Okay. But here's the deal: electrons are negatively charged, have no mass. Protons are positively charged, have a mass of 1. And neutrons are neutral, have a mass of 1. Protons and neutrons live in the nucleus. Electrons fly around the outside. That's the whole story. Let's go on. So, what we need to know now is, why do we care about this, right? So, atoms can be sorted into these different groups. So, depending on the number of protons or neutrons or electrons, we can have all these different types of atoms. So, what we're looking at here is the periodic table of elements. All of these elements are just different atoms, basically. These are the different types of atoms that exist. And atoms can also have isotopes, which we're going to talk about in a minute. Isotopes are a version of the same atom that's slightly different. So, we're going to look at those in a second. Okay. So, here's the deal: when you look at the periodic table of elements, you see a mass down here. This is the atomic mass of a hydrogen atom. It's 1.008 atomic mass units. So just barely bigger than 1 proton, right? Because hydrogens actually only have 1 proton and 1 electron. That's what's in a hydrogen atom: 1 proton, 1 electron. That's it. So up here at the top is something called the atomic number, and you'll see that on everything. So here's scandium, right? Has a mass of almost 45, has an atomic number of 21. It's the 21st atom, or 21st element in the order of the periodic table. If you read across from left to right and then down, it's number 21. 21 is its atomic number. Okay. Why does that matter? Well, we tend to write things in this special notation here. Why is there like a random A right there? There we go. Okay. Elemental symbol. There we go. We tend to write things like this. So this type of notation is called isotope notation. And we are going to look at that in a second. So what happens is we write the atomic number up here. We write down here. We write the mass number up here, and we write the charge over here on the right side. Okay. So C for charge, A for the mass number, Z for the atomic number. Now, the cheat codes for this is that the Z, the atomic number, is literally just telling you how many protons there are. So if we go back to our periodic table and we look at an atomic number, hydrogen's atomic number is 1, which means it has 1 proton. Helium's atomic number is 2, which means it has 2 protons. Iron's atomic number is 26, which means it has 26 protons in its nucleus, right? So whenever we see an atomic number, we know exactly how many protons there are, and that's what goes here in the bottom. Okay, so this bottom left number is how many protons there are. Then at the top left is how many is the mass, right? And we know that mass is made up of two things: neutrons and protons, right? So if we know the Z and we know the A, then we know exactly how many neutrons there are in the atom, because Z tells us how many protons, right? And Z plus neutrons is equal to A, right? So the A, the mass number, is equal to the Z, the number of protons, plus the number of neutrons in the nucleus. We'll look at that in a second. And then C over here is the charge. A lot of things won't have a charge, but some things do. And when you do have a charge, it is indicated there with a number and then a plus or a minus sign. I'll show you that in a second. It'll make plenty of sense. All right. So let's get into a couple of examples here. Let me show you some really simple basics. Okay, let's start with the simplest of all atoms. Okay, so this is hydrogen. Hydrogen has a atomic number of 1. It has an atomic mass, a mass number of 1. So if its mass number is 1, which is equal to its Z, 1, plus neutrons, there must have 0 neutrons, right? So we know this thing has 1 proton. So what does its nucleus look like? It's 1 proton like this. And we also know there's no charge over here, right? There's no value over here. So it must be a neutral charge, which means it must have a balancing electron. Okay, so that's an electron like this. In fact, you know what? Let's just write it like that. Let's just write it like that. And this is a proton like this. That's literally a hydrogen nucleus or a hydrogen atom. So let's just say this is the nucleus, right? There's the hydrogen nucleus. There's the electron flying around the outside. Boom, done. That's it. Now, I want to introduce the concept of isotopes. And there's a reason that we write this as isotope notation this way, because isotopes are it's just a fancy word that means it's the same atom, same element, right? But different number of neutrons. Wow. I totally goofed that up. I'm so sorry. There we go. As I did it again. There we go. So something to note about isotopes is that the atomic number for these isotopes is always going to remain the same because the number of protons dictates which element we're looking at, right? So if you have 1 proton, you got to be hydrogen no matter what. If you have more than 1 proton, you can't be hydrogen. It's not possible. So here we've got a hydrogen atom that has 1 proton in the nucleus and has an atomic mass of 2, which means it has 1 proton plus 1 neutron, right? So we're going to add a neutron to the nucleus. And we know it doesn't have a charge over here, right? Since it doesn't have a charge over there, we know it has to have an electron flying around the outside as well. 1 positive plus 1 negative, neutral. Boom, done. Does it have a atomic mass of 2? Yes. Does it have all the parts it needs? Yes. Okay. These are isotopes. Okay. These are called isotopes. And an isotope are versions of elements that have the same number of protons, but they have a different number. There's going to be a little lag here. Hold on. They have a different number of neutrons. Okay, now we can go one step further here. We can actually go out pretty far with this, but imagine a situation, right, where we've got H1, just like always, and it has a mass of 3. Wow, that means we must have what? Neutron, neutron, proton, and we must have a matching electron flying around the outside, right? Here we go. So this would be our nucleus in here, and this would be our electron buzzing around the outside. Okay, does that make sense? I hope it does. Those are isotopes, and that's the reason why isotope notation matters. Now, let me show you about charge really quick, okay? So let's look at another example here. I'll leave this stuff up here so y'all can see. So let's talk about iron, okay? Let's talk about something easier. I don't want to talk about iron. It's too complicated. It's just too big. Let's talk about carbon. Carbon, oh, there we go. Carbon has a atomic number of 6, which means it has exactly 6, 1, 2, 3, 4, 5, 6 protons in the nucleus, right? If we give carbon a mass of 12, that means it would have 6 matching neutrons, right? So it would have neutron, 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 neutron. Boom. That's the nucleus of carbon. It's happy. Okay, has 6 of each. Now, would they be oriented this way? No, they wouldn't be in this nice, neat, even pattern like this. It'd be slightly different looking, but that's fine. We'll just go with it. Okay, so that's the nucleus of carbon. Now, we know also there's no charge up here, right? Which means it needs to have how many electrons around the outside? That means that we need to, and let's just dash in some energy shells here for funsies. Pretend that's a circle and pretend that's another circle. Okay. So remember I told you earlier that there are these shells, these energy shells or these orbitals. The thing about the orbitals are that electrons don't actually live right on this orbital path. They don't. They don't just live here and fly around like planets around the solar system. But they're going to for the sake of this because it makes it easier to discuss, right? So let's say, okay, there's an electron here and an electron here. That's 2, right? We know we need to have how many electrons, by the way, right? We've got 6 protons. So we need to have 6 electrons, right? So then we'll put 3, 4, 5, 6. Okay. That is a neutral carbon atom. And the reason I only put 2 electrons on the inner circle is because the innermost orbital can only have 2. That literally doesn't matter to you right now. I'm just telling you because I'm a chemist, right? I'm a chemister. That's what it says on my degree. I'm a chemist, and it's important for us to indicate correct things. Anyway, blah blah blah. Here I am telling you that orbitals exist, right? Okay, so let's say that instead of having a neutral carbon, we instead had a carbon that is 2 plus, which means it has an overall charge of 2 positive, which means it has 2 positive charges more than it has negative charges, right? And remember, all of these little dudes are electrons. In fact, I'm going to erase them all and replace them with the electron symbol so that y'all can see that they're all electrons and they're negative. So we've got 6 of electrons and 6 of protons. In order to get 2 positive, we need to erase 2 electrons. Boom. So how many electrons have we got? 1, 2, 3, 4. Boom, we're 2 positive, right? Hopefully that makes sense and is fairly straightforward. What if we had a 2 negative charge? Well, then we would have add our 2 back in, right? So now we're at neutral, 6 and 6. How do we make it even? Or how do we make it 2 negative? We add 2 more negative electrons, 2 more electrons. 1, 2, 3, 4, 5, 6, 7, 8 total, and 8 is 2 more than 6, and there we go. That's our charge. Okay, so when you see things like that, that's how you work with that. Okay, so that's what you're going to see when you're looking at the notation for some of these things, and hopefully that helps you figure out how to get Z, how to get A, how to get protons, how to get neutrons, how to get electrons. Now, given some of this information, you should be able to figure out the rest, right? So I've been giving you the atomic number and the atomic mass, or the mass number, right? So mass number up here, atomic number down here. So, using this information, you ought to be able to then go through the provided worksheet and try and kind of figure out what's going on. So, what you're going to be doing in that worksheet is trying to count how many protons, neutrons, and electrons there are, getting used to this isotope notation. If you do go to look at the periodic table's notation is not isotope notation because it's not showing you isotopes. It's just showing you the bare stats of the element. Okay. But let me give you a little clue on P table here. P table actually tells you here's the atomic number, right? Here's the atomic mass. If you round it, you can get pretty close. So if there's 26 of these protons, how many of these things should be neutrons, right? So if there's 56 atomic mass, then there should be 30 neutrons, right? Then over here, it tells you how many electrons are in each energy shell. So we've got 2 plus 8 plus 14 plus 2. This is a really complicated example. Let's use oxygen. There we go. 2 plus 6 is a total of 8 electrons. Oh, look, there's 8 protons. That's perfect. That matches. That should be true always, right? So keep that in mind, unless you're looking at something that's charged. Okay. So good luck on that. And I hope it goes well.